Hello and welcome to our series of lectures on finite state machines. There are many different types of finite state machines. The one that we'll talk about in this series of lectures is in regards to detecting sequences of numbers. So we'll talk about what a Moore state machine is and what a Mealy state machine is using a sequence detection number. And what we're going to do is we're going to try to detect the input sequence of the numbers 110. So the binary combination 110, we're going to allow overlapping states. And so we'll talk about what that means as we go through the lecture, what overlapping states mean. When we create this state machine, right, we're going to start with a Moore state machine. It's a little easier of the two, the Moore and the Mealy. We'll create what's called a state diagram, a state transition table. We'll talk about detecting overlapping sequences. Then we need to take a look at what flip-flop excitation tables are, because what we want to do is we want to implement this finite state machine with D flip-flops, JK flip-flops, and T flip-flops. Right. After we do that, the last segment then will cover Mealy finite state machines to detect the same sequence. We'll do the same thing with the Mealy. We'll form a state diagram, transition table, and it will work the same. We'll allow overlapping sequences. Right. So first of all, what is a state diagram? And in particular, a Moore finite state machine diagram. Right. So for our sequence detection, let's start out with a problem statement. We're going to create a Moore finite state machine that detects the input sequence 110. Overlapping sequences are allowed. That would be the problem statement you might be given with your homework. Right? The objective is to detect when the sequence of input bits is first a 1, followed by another 1, and then a 0. So we can assume the stream of bits comes in, right? We want to detect, first we see a 1, then we see a 1, then we see a 0. So this is the order we want to detect from left to right here. We can have lots of different input sequences, right? We could have 0, 0, 0, 0, 0, 1, 0, 1, 0, etc., right? Many different sequences. We only care about 1, 1, 0 in this state. And so our hardware output will be a 1 when we detect this particular input sequence. If we have any other input sequence, such as the 0, 0 sequence, we're going to then, our circuit will output a 0. Our circuit's going to give us a 1 whenever we've seen the sequence, a 0 when we have not seen the sequence. We have to define our states. So a finite state machine, gee, surprise, surprise, it has a finite number of states. We always start from some sort of known initial state. So we can create this initial state. Sometimes that might be caused we'll call that the reset state. And so if we issue a reset on our state machine, that will always cause us to go back to that initial state. And we want to give the states names. And what I'm going to do is I'm going to name the initial state as 0. You'll see examples where states can be named A, B, C. You could name them Bugs Bunny, Daffy Duck, right? Whatever. I'm going to name them S for state, 0 for state 0, right? We always start counting at 0. Now that we have a known starting state, what we want to do is we want to determine the total number of states we need to recognize the sequence 110. The way the state machine works, the input will be a single bit for each clock cycle. We're dealing with sequential circuitry now. We're dealing with clock-driven circuitry. We'll actually be using flip-flops to implement our state machine design, right? That's why we'll have a clock cycle then it will actually input the number, evaluate what needs to be done. So a single bit per each clock cycle. So the first bit we want to detect is a 1. When the input is a 1, we want to transition from the initial state S0 to another state that represents receiving that input sequence 1. And so we can start then defining our states. Like I said, we started with this state S0. That was our initial state. So all I'm doing here in this table is I'm giving you the state name and a description of the activity that has caused us to be in that particular state. Like we said, we determined S1, the name S1. I gave that a meaning of we recognize the sequence 1. So we said when we're in S0, our initial state, right, the first bit we wish to detect is a 1. So we're sitting there in state S0. We look at the number that came in. We say that that number was a 1. That means we want to leave the initial state and go to a state that recognizes we received that first 1. And sometimes we say got 1, right? Our input was a 1. All right, so we have these two states defined now. What we can do as well, we have sort of this state table where I'm naming the states and I'm describing what they mean. We can start creating the state diagram. So the state diagram is a graphical representation of our state machine. We typically show the state names in circles. Inputs cause transition from the present state to the next state and are shown by directed arrows. For a Moore state machine, outputs are shown inside the state circle. Right? In a Moore machine, outputs are only a function of the present state. So the state machine output, as we'll see, is a function of whatever state we're presently in. So we're going to start our state diagram by drawing state S0. We're naming our output of this circuit Z. We could name it F. Traditionally in our combinational circuits, we name things F. In this case, our output is Z. So we write this first circle in our state diagram. We put the state name here, S0, and we put then I'm putting the name of the output Z and saying that it's equal to 0. Right. Now we want to add on our state transition from S0 to S1. So like we said, we started the state diagram by drawing the S0, saying what our output Z was. We define state S1 as when we get an input of 1. So we need to have names for our input variables. So our input variable is going to be named X, right? We draw the second circle here, S1, and we say then we draw the directed arrow that says we transition from state S0 to S1. So our directed arrow says we go in this direction. And then we're putting what caused that transition, the fact that X, our input, was 1, causes the transition to go from S0 to S1. Now, when we're in state S1, if we want to think about what our output Z is, remember our goal is to detect the sequence 110. When we're in this state, we've only detected a 1, so our output Z is going to be a 0 at this point. Right. So now that we have states S0 and S1, right? So now we say we're in state S1. We want to know what the next valid input in our sequence is. And in that case, it would be a 1, right? And so if we're in state S1 and we receive a 1, then we want to transition to state S2, right? So we have this third circle for S2. State S2's description is our input that we've seen so far to our finite state machine, our input is 1, 1. We know that when we're in state S2, we've seen a pattern of 1, 1. Right. Remember, these bits come in one at a time, but our state machine has some memory, right? Its memory then, when we're in state 2, what it's saying is it can remember, we only got here because we've seen X is a 1 the first time. So we're in state S0, we received a 1, we went to state S1, we received another 1, we went to state S2. So state S2 says, in this case, we have now seen the sequence 1, 1. The circuit output is a 0 at this point because we have not seen the full sequence of 1, 1, 0. All right. Now we have 3 states. What we want to say is we're in state S2. What happens next? So in state S2, the next thing we would like to see is a 0. Remember, we're looking for the input sequence 1, 1, 0. So when we're in S2 and our input X is a 0, we transition from S2 to S3. State S3 then, its description is input is 1, 1, 0. And here our output Z is a 1 because in state S3, the only way we can get to state S3 is if we've seen the sequence 1, 1, 0. That's the sequence we want to detect. So our output of our circuit in this case is a 1. We have then these states defined so far. Right, state S0 is our initial state. State S1, we go there when we've seen our input has been a sequence of just 1. We go to S2 when we've seen 1, 1. We go to S3 when the input has been a sequence of 1, 1, 0. Right. These are the total number of states we need in our finite state machine. So when you're developing a finite state machine, a more finite state machine, one of the best ways to do it, right, is to say, what is the sequence we need to detect, right? How many states do we need to detect this sequence, right? After we've detected the sequence that we want to see, we need to go back and deal with the cases of, well, what happens when we're in state S0 and our input X is not a 1, when it's a 0? So that's why I say here, our next step is determining the state transitions for the other input values that we might see while we're in each state. Like I said, here's where we left off. Here's our states, S0, S1, S2, S3. Here are our transitions, but we need to then, in each state, then we need to define what happens when X is its alternative value, right? So in S0, I said we've accounted for an input of X equals 1, right? When X equals 1, we go from S0 to S1. But what happens when we're sitting here in state S0 and X is a 0? What do we want to do? Well, when we have a 0 input, we ask, does the sequence 0 match any of our states? Meaning, in our state description, do any of these states say, well, I've recognized just the 0 so far? No, they don't, right? The sequence 0 doesn't match any of our states, right? If you go back here, right, S0 is our initial state. S1, that state says we've seen a 1. State S2 says we've seen a 1, 1. State S3 says we've seen a 1, 1, 0. So when we're in our initial state and our input is 0, we're actually going to stay in that state. So in S0, right, we said then the sequence 0 doesn't match any of our states, so we don't transition to another state. So when we're in S0 and X is a 0, we stay in the state. So usually we draw an arrow to show that, like a little arrow that circles back to the same state that says, okay, when our input X is a 0, we stay in the state. So once again, a directed arrow. Above that directed arrow, you put the value of your input. Now, sometimes you won't see the name of the input. Sometimes you'll just see a number sitting here. When I created these examples, I want to keep track of what's the name of our input, what's the name of our output. So that's why I like to put the input variable name on here as well. All right, so now we're done with state S0, because state S0, right, we know our finite state machine has one input named X. And we've accounted for what happens when X equals 0 and what happens when X equals 1. What we can do now is we can move on to the next state, S1, and say, okay, what happens when X equals 0 there? And so as we move through, that's what this slide is saying, right? We've accounted for both of these. Let's go ahead and account for all the others. So now, when we're in S1, right, that means we've gotten to S1 by seeing the sequence. So if we go back up here, with less arrows, remember S1 is this, says we've seen the sequence of 1. So when we're in S1, what this is saying is, when in state S1, we've recognized the input sequence 1. When we're in state S1 and receive a 0 input, what happens? Well, that means we've seen a sequence of 1, 0. And we say, do we have a state that represents input 1, 0? No, we don't. This state is initial. This state represents 1. This state represents 1, 1. And this state represents 1, 1, 0. We don't have a state for 1, 0. That means we want to transition back to the initial state S0. Right? That's not the sequence we want to detect. We then say, okay, we got the 0. We're going to go back to this initial state. Because if you think about it, if we get another value after the 0, suppose we get a 1, 0, 1. Well, do we have a state for 1, 0, 1? No. If we get a 0 after this, do we have a state for 1, 0, 0? No. Basically, if we're in this state and we get a 0, we have to start all over again looking for that sequence of 1, 1, 0. That's why we say here, we draw the directed arrow that says if we're in state S1 and our input to the circuit is a 0, we're going to transition back to state S0. Right, so we've accounted for S0 and S1. we need to account for S2 next. We need to say, what happens if we're in S2? So in state S2, remember, we get there because we've recognized the input sequence 1, 1, right? We're here because our input sequence is 1, 1. We've already handled the case of what happens when X is equal to 0. We need to handle the case of what happens when we've seen X equal to 1 in this state, right? So that's what this is saying. When we're in S2, we've already recognized sequence 1, 1. What happens when we're in state S2 and receive a 1 input? That means the sequence that we've seen so far now is 1, 1, 1. Do we have a state that represents input 1, 1, 1? No, we do not. And so what we're going to do is I said here, we're going to remove the leftmost bit from the input sequence 1, 1, 1. Right, so the leftmost bit is this 1, and we're just going to then look at the remaining bits in the sequence. So I say we look at the two rightmost bits, 1, 1. These are the two remaining bits in the sequence. And we say, do we have a state that represents the sequence 1, 1? Yes, we do, the state we're actually in right now, S2. So we say in state S2, when the next input is a 1, we stay in state S2, recognizing the overlapping sequence 1, 1 of the input 1, 1, 1. So what overlapping sequence means is that if we don't have the exact sequence we want, we don't return to the initial state. We're actually going to we're going to say that this one here could probably represent the start of a new sequence. If we're not allowed to overlap sequences, like I said, we would return to state S0. So if the problem statement did not allow for overlapping sequences, when we detected 1, 1, 1, we'd say we don't have any state that recognizes 1, 1, 1. We must transition back to state S0. But we're going to then allow these overlapping sequences. It makes our state machine actually work faster if we do this. Right? We don't have to go back through and wait to start all over. Right? We allow this to possibly be the start of a new sequence. And so that's why what we mean by overlapping sequences is that we're allowed to use some of these numbers overlap in there more than once. All right. So here's our updated state diagram, right? We said that we were in state S2. When our input X was a 1, we want to stay in state S2, meaning we still recognize that we've seen 1, 1 to get us here. Finally, our last then state transition is we need to account for what happens when we're in state S3, right? When we're in state S3, we haven't decided what happens when our input X is a 1, our input X is a 0. Right. So we'll start now with the state transition. We're in state S3, right? That recognizes, and what happens when X is a 0? So remember, in state S3, we got here because we've seen 1, 1, 0. Right? That's what this slide is saying, is that, right, in state S2, when the next input is a 0, sorry, this should be, let me correct that typo. It should be state S3. All right. So in state S3, when the next input is a 0, that means we've seen the input sequence 1, 1, 0, 0. And we ask, does that match any of our states? No, we don't have a state that recognizes 1, 1, 0, 0. We're going to remove this leftmost bit. Right? That's the oldest bit in the sequence. So we remove this and we say, do we have a sequence? So remove the leftmost bit and consider the sequence 1, 0, 0. Does this match any of our states? No, it does not. So now we remove the leftmost bit from the 1, 0, 0, and we consider the sequence 0, 0. Does this match any of our states? No, it does not. So we remove this leftmost 0, right, and we consider the sequence 0. Does this match any of our states? No, we don't have a state that just got 0, but we do have that initial reset state then, right? If we were to remove this 0, we want to say, we're going to transition back to state S0 whenever X is equal to 0. Right. So here we add this to our state diagram. We said here we're in state S3. When X is a 0, we're going to transition back to that initial state, right? Because basically we're starting all over with our pattern to start recognizing the next sequence of 1, 1, 0. Now, we need to handle one last state transition. Here when we're in S3, what happens when our input X is a 1? Right. So when X is a 1, remember we got the state S3. State S3 represents the sequence 1, 1, 0. And now we tack on what came through for X. X is a 1, so we have the sequence 1, 1, 0, 1. And we say, does that match any of our states? No, it does not. So we remove this leftmost 1, remove the leftmost 1 and consider the sequence, the right sequence 1, 0, 1. Does that match any of our states? No, it does not. So we're going to remove the leftmost 1 from here and consider the sequence 0, 1. Does that match any of our states? No, it does not. We're going to remove this leftmost 0 and consider the sequence 1. Does this match any of our states? Yes, state S1 recognizes the fact that we've seen 1, 1. Well, now our state, we add this directed arrow to our state diagram. When we're in S3 and our input X is a 1, our transition is from state S3 to S1. This now completes our state diagram because for each one of these states, we've determined what the transition should be whenever X is a 0 or X is a 1. And this is a completed Moore state machine diagram. Right? We know what our outputs are in every state. We know what the transitions are for when we get different inputs coming through. What we're going to do next is we're going to use this state diagram to build a state table. And the state transition table is going to then list the present state, what the values of our inputs are, and our next state values and our outputs. All right. Now I'm going to stop this portion of the lecture here. We'll pick up then in the next video how to create the state transition table.